Hi everyone, welcome back to ANR Academy. Today we are going to discuss maxima minima inequality from the topic definite integrals. Here let us see the statement. If small m and capital M, they are global minima, global maxima values of the function f of x, which is defined on closed boundary a to b, then here the inequality we have small m multiplied by b minus a, which is always less than or equal to integral a to b f of x dx less than or equal to capital M of b minus a. So this is the inequality in definite integrals. Let us discuss the proof. Given that the function which is defined on closed boundary a to b, let us draw a figure. Yes, on x-axis, suppose here it is small a and here it is small b. The function f of x is defined only in this closed boundary. Suppose that the function is defined in this way. Here a and here it is b. Yes, the function defined on closed a comma b, it has maximum value here and here. The maximum value of all maximas is known as global maxima, so that I am going to indicate global maxima with the notation capital M. Next, here also you have maximum value 1, 2, 3 maximas are there, and from the 3, middle one is maximum of all maximas, so that the notation here capital M selected. Next, the function has minimum values here, here and here, and from these 3, minimum of all minimas is known as global minima, and suppose the notation is small m. In the statement we have small m, capital M are global minima and global maximum values of the function f of x defined on closed a comma b. Yes, with that condition this is the graph. And now observe in the figure, suppose if you draw a tangent at capital M, and now observe the area under this line only on defined domain closed interval a to b only. Next, I am going to write area under this line with boundaries x-axis, x equal to a and x equal to b. That is, this area I am going to find now. We know that it is of rectangular shape. It is having maximum height capital M and it is of width b minus a. Or you may treat capital M as width, b minus a as length. That I am going to write here area of this rectangle capital M of b minus a. Next, now I am going to draw tangent at small m. Here I am going to draw tangent. Now observe the area under this line. This area I am going to find now. It is of height small m. Why? Because here you have the height small m. Next, width as it is, length as it is, height small m, width height small m and length b minus a. And now area of this rectangle shaded with white color, that is small m of b minus a. Next, we know that suppose this is the function f which is defined in the interval a to b, then the area under the function f of x this region, this shaded portion, area under the function f of x, that can be expressed as integral a to b f of x dx. The same I am going to apply here. This is given function which is defined in the closed boundary a to b. Now I am going to find area under this curve, this portion. Here the boundaries are the function f of x as well as x axis, x equal to a and x equal to b. This stars region area under the function, that is denoted by integral a to b f of x dx. Observe here, yellow colored area compared to stars area, that is greater, and white colored shaded portion least compared to remaining two. And equality holds when they are of same height. Global maxima suppose equate to global minima, and the function also constant function, then in that case maybe there is a possibility for equality. So I can write the relation here, small m of b minus a less than or equal to integral a to b f of x dx less than or equal to capital M of b minus a. Here small m, capital M they are global minima and global maxima of the function f of x, which is defined in the closed boundary a to b. Let us discuss an example. Suppose if you have the question, estimate integral 0 to 1 e to the power of x square dx. This is the question. Integration of e power x square in general, it is not possible to find, but we can estimate the result. That is, you can estimate the maximum value and minimum value. In between them there is a chance. See, directly there is no integral value of e power x square, but here the function f of x is clearly e power x square. Its derivative e power x square into 2x. To get maxima and minimum values, we have to equate its first derivative with 0. Then what happens? We get e power x, that is always positive, e power x non-zero and non-negative. So there is a chance to get just x equal to 0. It has stationary point at x equal to 0, and also given it is defined only in the boundary 0 to 1. So next limit you have to select 1. Particularly at x equal to 0, functional value become e power 0, that is 1. Next, at 1 it is e power 1, that is e. Stationary points at x equal to 0 and at x equal to 1. Maximum of maxima is capital M, minimum of minima is small m, you have to select. So this is the maximum value capital M and this is small m, e value approximately 2.718. Now by this inequality I am going to write small m of b minus a, which is less than or equal to integral a to b f of x dx less than or equal to capital M of b minus a. Here lower limit a 0, upper limit b 1. Substituting in this, already you have small m and capital M values. Small m is 1, b minus a, that is 1 minus 0 less than or equal to integral 0 to 1 e to the power of x square dx less than or equal to capital M, that is e, b minus a value 1 minus 0. On simplification we get 1 less than or equal to integral 0 to 1 e power x square dx less than or equal to e, and hence the estimation of integral 0 to 1 e power x square dx is, the value of this integral lies between 1 and 2.718, that is Euler number e. This integral value we are going to estimate, but we can't say exactly, but we can guess that the value must be in between 1 and e. This is the result. So in this way we can estimate some of the integrals which are not integrable. I hope you have understood everything. The students, those who are watching my videos, please subscribe the channel and don't forget to like, share and comment. Thank you so much.